Let's talk about limits as x approaches either infinity or negative infinity. So my first two examples here kind of represent one type of this limit where you're not actually doing any fancy like strategy or anything or computation. You're just sort of thinking about what must be happening at the ends of the graph. So for example, here we have the limit as x approaches infinity, 3 over root x. So I may not know exactly what this graph looks like, but I know as I plug in larger and larger values for x here, I'll have 3 over the square root of a million, 3 over the square root of a billion. So this is a constant numerator over a denominator that's getting infinitely large. And that case always goes to 0. So this limit is 0. So anytime you have just a fixed number over something getting bigger, bigger, bigger to infinity, that limit will always be 0. We have something similar in this second example, although it's a little bit more complicated because it's within a composition. So again, if I knew what the graph of 2 raised to the 1 over x power looked like exactly, I could look at the far right end of it because x is approaching positive infinity and make a decision that way. But I don't know what that graph looks like, so I have to figure this out a different way. And what I'll do is zoom in on the 1 over x part, right? Think about as I plug in very large values of x, I don't know what all of this is doing, but that part of it fits this description, right? Because I have a fixed number on top and a denominator that's going to get bigger and bigger and bigger. So all of this goes to 0. So my limit is just going to be 2 to the 0 that I just decided, which is 1. All right, so that's one way that we can compute limits as x approaches one of the infinities. And then we also have one other fairly common trick, which is you can kind of see the two examples coming up here. So here we have x approaching negative infinity of this rational function. So there are two ways to answer this question, and they both lead to the same answer, which is 2. Right, so one way is to remember that we know a lot about rational functions. We know about their asymptotes and holes and horizontal asymptotes, right? So what I could do is think, what is the horizontal asymptote situation of this graph? The top and bottom are both degree 3. So I can do the thing where I just look at the leading coefficients and I say 10 over 5 is 2. That tells me that this rational function has a horizontal asymptote at y equals 2 on both ends of the graph, particularly on the left end, so my limit's 2. The other more elaborate way to do it is obviously overkill, since it's going to be more work than what I just did to get this answer, but I'm going to show it here because of the example upcoming. So when we talk about a limit of a function like this, it's not a rational function because there's a square root in there. So then we can't use the shortcut and we have to use the more elaborate trick that I'm about to show. Okay, so we'll rewind. We know the answer is 2, but let's compute it in a way that will work in a lot of cases like this one. So what I'm going to do is think about plugging in really large negative numbers. And I'm seeing this x cubed. So we just have very large magnitude top over very large magnitude bottom. Technically, they both come out negative, but the negatives cancel. So this is kind of an infinity over infinity limit. And that tells me this trick, dividing the top and bottom by a power of x is probably the thing to do. So I want to divide the top and the bottom by some power of x. And typically we want to choose the largest power of x that we see in the denominator. So in the denominator, the highest power of x is the cube. So that's what I pick. I'm going to divide the top by x cubed and the bottom. So as long as I do the top and the bottom, I'm keeping it balanced. And in the next step, I'm going to distribute these into each set of parentheses and simplify everything as I go. So I'll keep my limit the same. All right, so this first term is 10x cubed over x cubed. So the x cubes cancel and I just have 10 left. The next one, I would have 3x over x cubed. So a pair of x's cancel and it ends up 3 over x squared. And then finally, 1 over x cubed does not cancel. On the bottom, we do something similar. 5x cubed over x cubed, they fully cancel and it's just 5. 9x squared over x cubed. The x squared cancels with two of these x's down here, and then there's one left over. So this becomes 9 over x. And then we kind of reevaluate the situation. Now that we've weighed everything down, we shouldn't have as many big numbers going to infinity. And in fact, 3 of these 5 terms go to 0 using this same shortcut from up here. Anything that's a fixed number over something getting large in magnitude will go to 0. So for example, 3 over x squared, even though we're approaching negative infinity, it's large magnitude numbers. So it's still 3 over bigger and bigger and bigger. So that goes to 0. Same thing here and here. And then the 10 and the 5 are just 10 and 5, right? So this becomes 10 minus 0 plus 0 over 5 plus 0, which of course computes to the 2, which we knew from the beginning was the answer. But again, this is the model that we're going to use for this last example. All right, so on that note, let's move into this final example. The phrasing of the question is a little bit different just for the sake of kind of connecting horizontal asymptotes and limits one more time. So anytime a question asks you to find the horizontal asymptotes, what they want you to do is compute the limit of your function as x approaches infinity and the limit of your function as x approaches negative infinity. So for rational functions, those always come out to the same number, so only one is sufficient. But for other functions, like this guy, these will come out to 2 different numbers. So over here, we'll say, oh, I have a horizontal asymptote on the right end of the graph, y equals my answer. And then when I finish this one, I say, oh, I have a horizontal asymptote on the left end of the graph, y equals this number. And they're going to come out to different numbers, which is interesting here. Okay, so let's start with the limit as x approaches positive infinity. So limit as x approaches infinity, and I'm going to grab this whole formula. Again, I have an infinity over infinity situation, right? Just everything involved is getting bigger and bigger and bigger. So I'm going to bust out this like one major technique that we have for this case. I'm going to divide the top and bottom by the highest power of x I see in the denominator, which in this case is just plain x. So the top gets 1 over x, the bottom gets 1 over x, and I want to distribute those into the parentheses. Right, so 2x over this x, the x's cancel, it's just 2. And then I want to get the 1 over x inside this root so that it can cancel. So what I'm going to do is decide like, all right, if I have a 1 over x and I want it to be in a root, I'll have to square it, right? So 1 over x is the same as the root of 1 over x squared. So that's what I'll do in this step. So I keep my root. 1 over x on the inside of this root is a 1 over x squared. So then if we simplify it, it would go back to 1 over x. And then in my next step, I'll distribute it into the x squared plus 5 in there. All right, the denominator works normally. 6x over x is 6, and then minus just 5 over x. I'll distribute the 1 over x squared in here and simplify it in a similar way. X squared over x squared is 1, and then plus 5 over x squared. And this looks a little bit messier, but it has the same magic that this example did up here, right? Anything that's a constant over a power of x is going to go to 0. So that would be this part and this part. So I can put zeros in those spots and actually just compute a number from the rest. All right, so on the top, I have 2 plus 1 is 3. So that's 3 over 6. So 1/2. So one horizontal asymptote is y equals 1/2. And because we were doing the limit as x approaches positive infinity, this is the far right end of the graph. So this is your asymptote as you travel way to the right on your graph. It tapers out to a height of 1/2. Okay, so let's compute this second limit and see kind of the weird part, like how this comes out to a different number, even though it's almost the exact same work. All right, so now we're going to do the limit as x approaches negative infinity of this same formula we started with. again, we say, all right, negative infinity over negative infinity. I have one trick, divide top and bottom by the highest power of x in the bottom, which again is x. So the beginning phase of this looks identical. This times 1 over x, and this times 1 over x. So in the denominator, I'll fill in first. 6x over x is 6 minus 5 over x. All right, so when I distribute the 1 over x into the numerator, I have 2x over x becomes 2, just like in the example next to it. And then I again want to sneak the 1 over x inside the square root so that it can simplify and combine with the stuff that's in there, the x squared plus 5. The problem is this right here is what we were using to sneak that 1 over x inside the root. And this is actually, as I wrote it, this is only true if x is positive, right? So then like 1 over a number is the same as the square root of 1 over its square. So let's actually label this. So x is positive. This statement is true, right? So if we're approaching positive infinity, we get to use this. If x is negative, we actually have to adjust that thinking. So we still want to get 1 over x to be inside a root. And the natural thing is to say it's 1 over x squared. But think about like if this is a specific negative number, let's say like -2, this would be -1/2 on the left if I plug in -2 for x. And over here, I would have +1/2, right? So this square and then square root just kind of accidentally deletes the minus sign that was there. So all we would have to do is put an extra minus sign on the outside to kind of accommodate for that. That's the one thing that we have to keep an eye on here. So I'm going to have a minus sign now outside of the root so that this can sneak inside. We still have a 1 over x squared. The rest of the entire problem will go the same way. But because x is negative, this sign switches to a minus so that the x squared can get into the root. Right, let's continue the same way. We're going to get all the same stuff, but we'll have a minus sign right here. So I have 2 minus √1 plus 5 over x squared. And then I still have these same two pieces go to 0, but this computes differently now because of that subtraction. So on the top, we have 2 minus 1, and on the bottom, it's 6. So on the left side of the graph, as x approaches negative infinity, I have a horizontal asymptote of 1, 6.